Maxwell-Faraday's equation. Maxwell-Faraday's equation is one of 4 Maxwell's equations. Originally, the physical phenomena were studied by Faraday and established as Faraday's law, and Maxwell concisely described it in differential equation form. What it is basically magnetic field. The change of magnetic field produces electric field. So it's a generator. We can make a generator using this principle. Extract energy from magnetic field. Okay. So in the differential form, the magnetic field, vector field, the change over time, and don't forget this negative, is gonna cause curl E, electric field. This is all the vector function. So there is a vector coordinate, and each location of the space has certain B vectors, and this is E vector. And this curl usually causes the circular vector field. So this is a B, and E will be like that. So this imply this type of vector field. Okay. Now this is what I mean. You have a B, and vector field of E will be circle around it, and that's what the curl usually does. And now the B is going to change over time when you move magnet in and out to the loop of the conductor, and loop of conductors generate electricity, and the electricity is the function of this movement. Okay, so how it works, the same exact equation but integral form, time variant, and this is this kind of surface. Okay, that's a D, and the B integral by ds. ds is an element of this surface. Okay, so you take an integral over this entire area, basically collecting amount of B that go through this surface. Okay, and checking time change, and that's gonna be equivalent to what this is the line integral. See, D is associated with L, this loop, and you take the vector E and add up along with this line. That's what it is, line integral. And what this represents is a voltage, potential, V, right? Okay, so the curl E is expressed by the matrix, and this is unit vectors for each x, y, z direction. Okay, and derivative of each. So you know how you break this determinant. It's not actually matrix, it's a determinant. Okay, and this equation is something like Gauss equation. It's a vector field determined by derivative of potential field. This is a vector field determined by derivative of electric field, but here the cause is B. Okay, So B caused E. Now there's a curve theorem. It's called the Kelvin-Stokes theorem. This theorem is used to get this, because what you do is differential form, you take surface integral on the both side, this side and this side, the surface integral. But when you take a surface integral of curl E vector, it's equivalent to take a line integral along the border. Okay, and that's what the Kelvin-Stokes theorem is. So using this, we obtain this one. So that's why this line integral is coming into this Maxwell's equation. It was a surface integral of curl and changing to line integral of E. So the electric field, which direction is going to be induced? So what's happened is, you can think of this way. Suppose magnetic field amount is increasing, right? Okay. So what is negative? That means electric field is generated to reduce this increase. That's what it means. So if this is increasing, then to decrease, magnetic field is generated by the current, and this we have to look at the next equations, Ampere's equation. Current is induced this way, so magnetic field is induced this way, and that's against the increase of this speed. That's a direction. Okay, so in order to induce E in this direction, as you see on the diagram, this delta B has to be decreasing. Decrease. If this is decrease, then it try to induce magnetic field to increase. It's all come from this negative here. Okay, so in order to generate the magnetic field this way, the E is induced this way and the current flow this way. I hope you get this. This is very important to determine which direction, right? Okay, next thing's important is this boundary effect. The magnetic field doesn't have to change. B can be constant, but D can be time variant in this equation, right? Because dt is outside of this equation. Okay, that means even B is constant. If D change, then whole things change. For example, like a generator, you have a permanent magnet has a B going this way, and it's not changing, and you rotate this conductor. So what's happened is the D changed, right? B constant, D change by D0 constant sine omega t. So the V is alternate voltage 2LB D0 sine omega t. That's what the generator does. Okay, so that's the important point. So that's pretty much all about this Maxwell-Faraday's equation. And Faraday's law basically generate electrical field, and it's all concisely summarized in this Maxwell's equation. Okay, thanks for listening, and please check out the videos.